Hello, welcome to the last recap of the Cosmology from Home 2021 conference. Today we'll be recapping anything that we thought was interesting from the whole 2 weeks of the conference. Cosmology from Home is as it sounds in the name, Cosmology conference. Cosmology is the study of the properties of the universe, maybe when they're taken as a whole, when you're not looking at like individual stars and individual galaxies. Although when studying things like dark energy and dark matter, sometimes individual stars and individual galaxies become important. So yeah, the whole conference is up for grabs today. Whatever we found interesting, we're allowed to talk about. I'm joined by two other people today, Deanna Hooper and Matthias van der Wild. Do you guys want to introduce yourselves quickly? Deanna, maybe first.
Sure. Hello, everyone. My name is Deanna Hooper. I'm a postdoctoral researcher over at the ULB in Belgium. I study dark matter and the cool things that happen when we try to understand the matter that is invisible to us. It's a fun topic. Now, at this conference, I was a plenary speaker. I gave one of the plenary sessions. I've also been involved in a lot of ongoing discussions and, of course, in all of the outreach streams. As Sean mentioned, this is our 6th broadcast in 2 weeks. Not too many of us here today because everyone is just exhausted by the end of the conference, but we made it to 6 broadcasts, and I think that's absolutely awesome. So happy to be back here for the last day.
Thanks, Deanna. And Matthias.
Matthias van der Wild. I'm not currently, but soon based at Durham University, where I'm working on. Actually, I'm not even sure exactly what I'm working on, but I am going to build one of the infrastructures for the LOFA telescope. Before that, I worked as a postdoctoral or as a PhD researcher, where I worked on quantum gravity and tried to find some connections to quantum gravity with cosmological observations, which is very interesting in a way, because normally quantum gravity is this very formal game where you're not really sure if it will ever make any sense because there are no observations. But nevertheless, there are some reasonable things that you can say about things that you can measure.
Cool, thanks. And as per usual, I completely forgot to introduce myself. I am Sean Hotchkiss. I am a part-time postdoc here in Auckland, working on all sorts of aspects of cosmology. And yeah, maybe most recently, a little bit on primordial black holes, a little bit on trying to quantify the probability distribution of possible vacuum energies, which I might go into at some point in this stream or a future stream. Right, so we're recapping the whole conference today. I think Deanna volunteered to go first. What we'll be doing is just sort of talking to you about the things we found interesting. Feel free to ask follow-up comments as we go if we're not clear on anything. This isn't an AMA, so we might not get to any very general questions, but follow-up questions definitely strongly encouraged. So Deanna, what were one of the more interesting things for you during the conference?
So before going into that, I just want to say hello to everybody joining. Thank you for being here. Bo, Mark, Paul, always great to see you. Paul, thank you for your concern. I am close to the flooded areas in Germany. Me and my family are perfectly safe. My partner's family is all very safe. But yeah, it's basically one town over from where I am is flooded. But thank you for the concern, and yes, I am okay. So there have been a lot of really, really fun things at the conference. But before going into what I liked about last week and the first few days, I want to talk about something that has happened between our last recap and today. That was one of the theme discussions where participants of the conference proposed a theme, and if enough people were interested, the organizer scheduled it for us. There was a discussion yesterday on imposter syndrome. Now, imposter syndrome is that feeling that you get when you think that you're a fraud, that you're just kind of there by mistake, that people have accidentally hired you or accepted you, and someday they're all going to wake up, realize that you're a fraud, and get rid of you. And it's this kind of feeling that you're an imposter in the field and you're just pretending to be there. This is something that many people in our field experience, and many people in other fields. A lot of high pressure fields, people experience this. And it's something that is very noticeable to a lot of us. And it's also something that people don't talk about so much. But yesterday at the conference, we actually had a completely honest and open discussion where we were all allowed to just share our own personal experiences with imposter syndrome and discuss how we try to overcome it, what techniques we have, and just in general share this experience. And I thought it was really nice. There were about 20 people participating in the discussion, or 20 people in the room. Only about 15 actually shared their experiences, which is fine. Some people didn't want to. But it was people from all different aspects, from undergrads, PhDs, postdocs, all just discussing our own personal experience with this and just making everyone aware that this is a shared experience and something we all go through. So I think this was an extremely important discussion to have. It's also one of the only discussions at the conference that was not recorded for participants who couldn't catch it live, which I think also allowed everybody to just feel like they could be more open and relaxed. I learned a lot. We exchanged very useful coping mechanisms and strategies. And I think we all left feeling very positive about that. So it's not science related, but it's something that almost everyone in our field does experience. So I think that was a really, really important discussion to be had yesterday. And again, I'm very grateful for the organizer for scheduling this. And today we have two organizers up here on screen with me, so I can't really say anything bad about the conference. I'll save that for when they're not around.
Now's your chance to say things, because we can't kick you out of the conference in a bitter disappointment.
Yeah, you can't kick me out now.
Yeah, I couldn't attend the imposter syndrome thing because I was asleep. It was 3 a.m, I think, or 4 a.m. my time. And as you said, this isn't recorded, but my thoughts on that are, there's a couple of thoughts. My way of dealing with it is realizing that everyone else feels just as inadequate as I do, I guess. And then that gives you kind of confidence that you realize we're all kind of stumbling along. So it's not to realize that actually I'm brilliant after all. It's more just to realize that everyone else is kind of just as clueless when it comes to research and everything, that we're not, it's not that I'm the one who's like, how am I doing this? And everyone else is doing it perfectly fine. And my other thought on imposter syndrome is kind of that one of the main reasons it arises is that as soon as you understand something quite well, it starts to feel trivial to you. I think I remember we were having this discussion either in the conference or in the live stream the other day, that like my entire thesis, after I'd finished it, I could have reproduced my PhD thesis, reproduced in a couple of months. And that's not meaning to say like I'd become brilliant, but more just that you spend so much time when you're researching going down the wrong avenues, that once you found the right avenues, you can reproduce that relatively quickly. But that puts you in a situation where you feel useless, right? You're about to hand in your PhD thesis, and to you, it only feels like a couple of months worth of work. Of course, anyone outside of you will look at your work and be like, wow, that's really substantial. I couldn't do that. It would take me years to reproduce that. So it just constantly puts you in the situation where everything you understand seems trivial and everything everyone else understands seems really, really difficult, which is just like a ripe atmosphere to start feeling imposter syndrome. Do you have thoughts, Matthias, or?
No, I can sort of agree with that with you, Sean, that like it's something that a lot of people will struggle with, and especially if, so speaking from my own experiences, where you are basically just trying to do your own research and think about one problem for a very long time, then eventually it is very easy to come to the conclusion that after thinking about something for half a year, that the problem is trivial, and therefore all the things must be trivial, all the things you have done. And it is very easy to lose sight of all the things that you, all the insights that you came up with along the way, and all the things you've learned until then, and all the things that are not obvious, and all the things that anyone would struggle with. And I found it very helpful, or very, very, very nice and good that everyone also shared their ideas on how they manage and cope with imposter syndrome. And I think that a lot of the people who were there actually benefited from it a lot.
Cool.
Any follow-up thoughts, Deanna?
Well, I can share one of the coping mechanisms that I actually brought up yesterday for those who missed it and for anybody here who wants to know, which is creating a validation folder. And this can either be on your desktop or in your email. And it's just a folder where you put every single positive thing that has happened in your career. Like in our case, if your paper got accepted to a journal, even the email when you put your paper on the archive, keep all of these emails. Anytime a colleague has emailed you like, hey, good job on your talk or good job on this paper, you put it in this folder. Anytime you got a PhD offer or postdoc offer, anything like that, you just put it in this folder. And you could even name it validation or ego booster. And then anytime imposter syndrome is getting big and you're thinking, oh, what have I done? Do I deserve to be here? You go and you open that folder and you read through it and you check exactly all of the positive things you've achieved and why you are where you are. So that was my 2 cents added to the conversation as to what I try to do to help me with it.
Sounds like an awesome idea. Yeah. Wondering whether I might start doing it. Yeah, Matthias, unless you have more thoughts on the imposter syndrome, I might hand over to you for your own first piece of the conference you want to recap.
I mean, there's just one thing. That is not something I shared during the actual session, but something I realized that is something I do in order to combat imposter syndrome. So maybe the people that are listening now can actually maybe take something away from that. And that is that one of the reasons why I feel that the things that I have done are often very trivial is that it is very difficult to keep track of the progress that you make along the way. So what I often do is at the end of the day or maybe at the start of the week to write down a few things, like not in a computer, not in an email, but just physically write down in a book or on a piece of paper what the things are that I currently struggle with. Like, these are the answers that I am trying to find. These are the puzzles that more puzzle me. And at the end of the day or at the end of the week, to give in a few lines a brief update on how things have gone. Like, these are the things that I have done in order to find the solution. These are the things I have done in order to make that tiny bit of progress. And at the worst case, you see that you are progressively making efforts in order to find the solution to what you are currently struggling with. And at the best scenario, you also see the solutions that you actually came up with. So you not only see the progress, the actual solution, that you are able to come up with the solution, but you also see the way at which you come to the solution. And that was just the 2 cents that I had to give to this.
Yeah, cool. So
imposter syndrome.
Do you also want to talk about, I think, one of the sessions that was earlier today?
Right. So today we had a brief discussion, we had a dedicated discussion about curvature, and so we know that that space, as we described the universe using space-time, and space-time is something that is curved, not curved as you would imagine a piece of paper being curved in space, but it has some intrinsic curvature. And I found that a very cool discussion. There was a lot of people chiming in and a lot of people that were sharing ideas. And I found it very interesting also to think about the notion of local curvature. For example, in the solar system, space-time is curved because you have massive bodies. You have the sun and the planet and the planets in the solar system, but you also have the global curvature, which describes the curvature of the universe as a whole. And these two are not necessarily the same. And that was something that was, I mean, whether it gives you something useful in at that very moment, that is, you're never sure. But I found it a very stimulating discussion to have.
And what's one of the verdicts? Is the universe curved, or is it worth looking to see if it is curved?
That was also one of the very interesting things that was mentioned, because there is a limited, with your measuring apparatus, you have a finite resolution. So the question is that resolution enough to ever resolve whatever effect you have from curvature in the first place? And I think that sort of the at least passive consensus is that for the moment it is something that you should keep in mind, but there are still a lot of things that you can do without having to worry about any boundary conditions or any global effects that curvature may have. At the same time, it is also interesting that there are observations where they say that there is a possibility that the universe is curved, and what consequences does that have for the universe and as a whole. Like what does that tell us about the structure of not so much what that tells us about the structure of space, but what consequences does that have for our observations in the future?
Yeah, Deanna, I think you attended. You might have even been the one who suggested that discussion. Do you have some lingering thoughts from this morning?
Yeah, sorry, I just had a hair on my eye. I suggested this because actually, when I gave my plenary talk about CMB, one question that I was asked is to comment on any evidence from the CMB on curvature. And it was a fun conversation, and then it actually triggered a detailed conversation in the Slack group as well. So that's what prompted me to propose the topic, but I very much was happy not to host it and just listen to that one. And I thought it was very interesting because we do kind of have a lot of evidence that the universe is flat, but it was pointed out that any deviations from this would be extremely interesting. Because if we were to find a closed universe, the implications are that the universe is finite, which by itself is just like a paradigm shift in our thinking about the universe. So even though we currently don't have any evidence for curvature or any clear evidence, I think the takeaway message is that it's something that we should still check for in future experiments. We shouldn't include it by default in all of our models because currently we have no evidence for it. But we should always just recheck this assumption, because if we ever deviate from it, it's very interesting. So I thought it was a very fun discussion, and it was interesting to hear a lot of different perspectives. I also just want to shout out the PhD students who presented it. That was presented and hosted by Yanguan. And I know he's a bit nervous, but he did a great job. So I just wanted to shout him out for the great job in hosting that session today.
Yeah, Angaran has been present in a couple of the live streams. So if people want to catch him, watch the replays. So I know that there's some discussion in the conference about whether we should be suspicious about the fact that the flatness or the curvature is so close to zero. So the idea is that, okay, we've measured today that curvature is almost zero, that I think the dimensionless parameter must be less than like 1 in 100 of, or maybe a more intuitive way to think about it is that if there is a radius to the universe, the radius of curvature must be 100 times bigger than the currently observable universe. So it's very close to flat. And if you evolve a universe forwards in time, it gets more and more curved as time goes on. So therefore, if today the radius of curvature must be at least 100 times bigger than the current horizon, then in the past it must have been even more flat. And there is an argument one could make that this is surprising. It could be any number. Why was it so close to zero? But then there are counter arguments, apparently, that is not surprising. Does anyone want to have a go at kind of going into that in detail? If not, that's okay. We can just leave it at this.
I'm a tad too tired to take on that caliber of question. So
I missed the discussion, so I'm also, it's quite early here, so we can save that for a future discussion.
Yeah, let's save that for future work. It's left as an exercise to the reader.
Yeah, Paul, that's a good question. I'll just put it on screen. This is the first time I've ever presented something on screen, so let's see if it works. Yeah, it becomes more and more curved overall, not just locally. Locally would mean you'd have to be getting a more and more kind of dense local environment, which might happen. You might have a star form or a black hole form, and then locally it would also get more curved. But my statement about it becoming more curved over time was globally, like the entire observable universe is getting more curved. Whether it's open or closed, it's getting more open or more closed. I'm sure that at some point the CMB will appear. Not yet, but yeah. Okay, so I guess that's my turn now. My first thing I wanted to recap was we had a panel discussion. In fact, Matthias moderated this panel discussion, so hopefully he'll have some insights as well on primordial black holes and gravitational wave detectors. So what we wanted the panelists to be discussing was there are these gravitational wave detectors, LIGO, Virgo, and Kagra. And what they're doing is detecting, so far what they've detected is black holes that are colliding. As the black holes are kind of orbiting each other somewhere in the universe, they get closer and closer and closer. And as they're merging right at the very end, that's an extremely explosive event. And because of that, gravitational waves get emitted. and they're the kind of loudest things that emit gravitational waves with a wavelength that is what these detectors can detect. So we expect that astrophysical sources produce some black hole binaries that will orbit and then collide and then emit gravitational waves. These black holes are formed from things like supernovae, but for two reasons it might be interesting to consider they might be primordial black holes. First of all, there are some theories that predict that it should be primordial black holes. Second of all, there is speculation that there might be some mass ranges that it's difficult to produce black holes in astrophysically, and yet we are detecting them via these gravitational wave detectors. So then if one is naively not expecting astrophysical sources, but we're still seeing them, maybe they were primordial. So I found that a very interesting topic of conversation. Does anyone else have any thoughts? I mean, I can go into how we might expect the primordial black holes to form, but we can perhaps have your thoughts, the other panelists' thoughts, before I get to that.
I'm waiting for the recording of that session. I think it was 9 o'clock my time on one of the few evenings when we didn't have a broadcast. I crashed on the sofa that evening.
Fair enough. Matthias, what are your lingering thoughts from the panel?
I think it is very interesting that we got the different viewpoints from both the cosmology people and from the astrophysics people, because you can imagine that these two different groups want to have different sorts of knowledge, and they that make it somewhat difficult to sort of see in the observations what exactly is there. So getting sort of drawing the Venn diagram and seeing where the overlap is and trying to get sort of a mutual ground of understanding, and trying to, as a result of that, a conversation going that increases everyone's understanding about both primordial black holes or gravitational waves or whatever other observations that you can make that are related to those. I think that's very cool. It was an interesting discussion to moderate.
Yeah, and I think it was a difficult discussion to moderate, I can say, as an outsider.
Because definitely difficult, yeah.
Yeah, because these two groups haven't discussed much. And we tried to get them to kind of discuss in advance via email, and it wasn't super successful. Only a few people did that. So they didn't arrive with a kind of common language. But yeah, and I think because it was a slightly ambitious project to get these two groups to talk, that's why it was difficult. Yeah, my lingering thoughts from that were that both sides are kind of, the theoretical uncertainties are sufficiently large that it's not an accurate statement to say that there is this mass gap on the astrophysical side. There's just a uncertainty bigness. What's the opposite of a gap? But there's an uncertainty where you can potentially say there's a mass gap and potentially say it's totally fine. And so, and again, on the primordial side, trying to predict exactly what one should expect, a kind of mass distribution, this many primordial black holes in this mass, this many in this mass, this many in this mass, this many at this mass, is also very uncertain. So I'm probably going to get crucified by the cosmologists who work on primordial black holes, but it does feel like in that scenario, the Occam's razor simple assumption is that it's more likely that the black holes we know exist, the stellar black holes, don't have a mass gap than some exotic stuff is happening in the early universe. That's not to say it's not interesting to work on the exotic stuff, because we know that new physics has to come from various places, and some of these primordial black holes would come from certain models of inflation, and we don't know exactly. Inflation probably occurred, but if it did occur, we don't know exactly what caused it. So anything that might give us evidence about that is certainly worth working on. But if I was made to gamble, I certainly wouldn't bet on there being primordial black holes. Just waiting for the lightning strike or the angry army to show up at my door.
Yeah, I can do the angry part there. Do you mean like primordial black holes don't exist at all, or they don't exist today?
I think if there was a god who could come and make the judgment, I would bet on probably never existing at all. Because I guess you also then work on their effects in the early universe, don't you? For example, the CMB if they decay. Is that right?
On spectral distortions, yes, and
Yeah.
also on fun things like Lyman alpha. I actually have 2 papers with primordial black holes.
Okay. Well, I have a paper on primordial black holes as well, so I shouldn't. I'll show up at my own door, crucifying myself. So let's maybe go into what might cause primordial black holes to exist. So as the universe is evolving, there's a thing called a horizon, which is kind of how far any causal effect could have propagated since the beginning of the Big Bang. You have a kind of finite size that light could have traveled, and that size is growing in time. And if when a fluctuation in the density of the universe reaches that size, it is really, really large. So of order 1, the density in this region is twice the average density of the rest of the universe. So the density contrast is 1. It's the background plus 1 background. Then it's so overdense that before any kind of I want to use the word virialization, but that won't mean anything to the audience. Before any kind of inhomogeneities in this region of overdensity can start orbiting each other, they just collapse too quickly, and then they get dense enough that a black hole exists. And then once a black hole exists, you can't undo the black hole. So that's how primordial black holes tend to form. But you need then a model of the universe that will cause such a large overdensity. And then, yes, as I guess Diana was not implying, but hinting at, this phenomenon can happen at all sorts of different distance scales. So it can happen very, very, very early in the universe, and then you get quite small primordial black holes, or it can happen much later, and then you get quite larger ones. And then there's only a very small piece of the history of the universe where the primordial black holes would form at just the right masses that now LIGO and Virgo and Cagra would be seeing them. But these other mass black holes aren't in some kind of dark window where we couldn't possibly observe them, because you could, for example, observe them with things like the CMB. So do you want to maybe talk about why you might see spectral distortions due to primordial black holes, Deanna? Because I think that's an interesting side topic.
Sure, I just heard the word CMB. So a CMB map appeared, even though it was not relevant for the current discussion. So I'm taking it away again. I heard CMB. So yeah, I don't think we talked about spectral distortions much. So spectral distortions are tiny, tiny, tiny deviations to a perfect black body. Now, a perfect black body is something that emits at all possible frequencies. The most perfect black body that we've ever found is actually the CMB, which is really, really cool. It's really the most perfect black body we've ever found. But there are tiny, tiny, tiny imperfections in this black body. And this actually gives us a huge amount of information. Now, these tiny imperfections or deviations from a perfect black body are called spectral distortions. These can be caused by anything that changes the energy of the particles of light in the early universe, which is pretty much anything. So these tiny deviations, these tiny spectral distortions, allow us to study many, many, many different scenarios. They are predicted both within our standard cosmological model and in other models, which means measuring these spectral distortions at a specific amount would be a clear piece of evidence in favor of our standard model. It would be like a prediction that the model has made that we would be able to observe. A lot of other models predict other amounts of spectral distortions. Now, the thing is that these spectral distortions are extremely difficult to measure. It's really, really difficult to measure. The only measurement we have of these spectral distortions is from 25 years ago. We were not actually able to measure them. We were just able to put limits, like they cannot be larger than this amount, which was good for the time, but it was 25 years ago. And this is one of the places in our field where the theory has progressed much more than the experiments. Theoretically, we can calculate exactly how much spectral distortion each model should produce. This is something we can do. This is something that I worked on in my PhD. We wrote a code to do this. But we don't have an observation. I'm one of the people campaigning and just promoting spectral distortions because I'm really hoping that within my lifetime we'll get a mission that's going to go out there and measure these things. Because for sure they're there. And if we don't find them, what we know about cosmology is wrong. It's a proof of our model. So it's something that's just out there waiting for us. On half of my, well, about a third of my plenary talk last week was actually purely about spectral distortions. Now, bringing it back to the topic at hand of primordial black holes. Now, if these primordial black holes are formed in the very, very early universe, they can actually evaporate. This is a process known as Hawking evaporation, whereby you basically create a particle and an antiparticle right on the border, right on the horizon of the black hole. Now, this is something that happens commonly in the universe. You frequently create a particle and an antiparticle, they annihilate, and they return the energy they stole to be created. But if this happens on the event horizon of a black hole, one particle can fall in, another can escape. To pay back the energy that was taken to produce these two particles, the black hole slightly shrinks. So this is known as evaporation, Hawking evaporation, because it's evaporating. Just want to be very clear here that this is not something escaping from the black hole, because nothing can escape from the black hole. It's just particles being produced on the surface, one goes out, one goes in. This is a tough topic to cover. So if primordial black holes were produced in the early universe, they are evaporating via Hawking radiation. During this process, they would actually affect the energy of the CMB. I think our videos have just frozen, so I hope we're still alive. Let's see. Okay, we should be back now. Not sure at which point we cut off, so let's just recap here. We have these particles created on the event horizon. One falls in, one goes out, the black hole slightly shrinks. This is Hawking evaporation. Now, if this is happening in the early universe, this Hawking evaporation is going to change the energy of the CMB, which means it's going to produce spectral distortions. So we can use spectral distortions, if we were ever to measure spectral distortions, to try to backtrack and understand more properties of these primordial black holes. This was a big chunk of one of my papers on spectral distortions, where we considered if these primordial black holes are evaporating, what type of signal would they produce, and how sensitive would our mission need to be to detect such a thing. And we basically showed that if we have a mission that is already within reach experimentally, that we could build today if we had the money, we could exclude a large region of parameter space for these primordial black holes. So it is a way of testing primordial black holes. It's super, super fun. And it's a lot of dense topics there. So if anything wasn't clear, please do ask in the comments, because I can talk about any of those topics for hours very happily.
Yeah, I feel like we could stay on primordial black holes for the whole rest of the stream. I just wanted to maybe see if Matthias has some thoughts on one thing. You mentioned that a particle escaping a black hole due to Hawking radiation is not actually escaping it. I guess you and I, Deanna, are both kind of more cosmologists, and I'll explain what I mean by that in a second. And so it is true that in the realm of kind of people who are working on quantum gravity research, this becomes a very, very difficult fact, right? That something is escaping a black hole, and it's happening due to quantum mechanics, that, as you said, a particle and antiparticle get created, and then in pure general relativity, nothing can escape a black hole. But in a quantum mechanics, in a curved background, you do get these things kind of traveling past horizons, and then it raises issues about information, and can information escape a black hole, and trying to solve this problem about where does the information go that fell into the black hole once a black hole is evaporated is a thriving field of research. I was just wondering if, Matthias, if you know anything about that and wanted to share ideas about like firewalls and stuff like that. Sorry for putting you on the spot. It's okay if you're as much of an expert as us. I just suspected you might be a bit more of an expert than us.
I mean, I'm not really, as you said, I'm not an expert on this at all. It's one of those things that I'd always wanted to look into, but never really found the time to. It is just that the way I understand it, if you look at quantum mechanics, you don't look so much at things which have a definitive value, right? There are you have these indeterminateness relations. Like, you can't measure the spin or the position and the momentum of a particle simultaneously, and actually you can wonder whether or not there exists such a thing as a particle having a definitive position or momentum at all at any time. And the way I understood Hawking radiation is that you start from a black hole with a certain mass or a certain energy in space-time. And then you want to look at that quantum mechanically. And it turns out that it is possible that there is a transition from the state where you just have a black hole of the mass m to a second state where you have a black hole and a particle. And the particle will always have a certain mass. And as a result of the conservation of energy, or the conservation of mass, if you want to look at it that way, the black hole must have a lower mass in the second state than it had in the first state. And sort of heuristically, this is sort of the idea behind Hawking radiation, that like you often hear about these explanations where you have because of this indeterminateness relations, that you have particle-antiparticles which come into existence very close to the event horizon of the black hole, and the antiparticle falls into the black hole, the particle escapes, and because the antiparticle has a certain negative amount of energy in that sense, because you must have conservation of energy at every time, the net mass or the net energy of the black hole has to decrease once the antiparticle is absorbed by the black hole. But as I understand it, it is like that explanation is not quite correct, and you should actually think about sort of quantum states and the evolution between quantum states as you have a progression of time. I sort of think it may have gone on a tangent, so maybe I sort of wandered off your
No, I mean, I deliberately asked you to go on that tangent. I mean, I think, yeah, it's difficult to know what's happening. I mean, this is the possibly the greatest unsolved problem in fundamental physics at the moment. Quantum gravity is exactly what's kind of happening. Hawking radiation is kind of like the one tiny step we have potentially taken into quantum gravity, where we're actually just doing normal quantum mechanics, but in a curved background, I guess, back to this idea of space-time curvature. And so we feel like we're probably doing it correctly, but it's worth emphasizing that Hawking radiation and other examples of this quantum mechanics in a curved background, we haven't yet observed anything that has been predicted, not necessarily because the predictions are wrong, but just we haven't been good enough to devise experiments to make these measurements. Hawking radiation from black holes that are the sort of black holes we know of is negligible. They're too big. It's the small black holes that are giving off much more energetic Hawking radiation. So yeah, I mean, it's difficult, and it's difficult because it's actually also difficult, just people don't know the answers on the fundamental research side. So I think, was it Mark asked a question quite a while ago now?
Maybe before we go to that one, Paul has an on-topic follow-up question about this discussion. Okay. I'm not sure who wants to take it. The question is, why is it more likely a negative or positive particle would fall back in? If it is random which one falls in, then there wouldn't be evaporation.
Right. You mean, yeah, negative or positive mass. So that sort of ties into what I just said, right? Like this is usually how Hawking radiation is explained. That because nothing has a definitive value at any given moment in time. It's only when like quantum mechanically, you can only talk about averages having a definite value. But Hawking radiation is often explained in terms of particles and antiparticles coming into existence and annihilating simultaneously, or shortly afterwards. And when that happens near the event horizon of a black hole, the conventional explanation is that an antiparticle forms closer in some sense to the event horizon and falls into the black hole, whereas the particle escapes. It escapes the attraction of the event horizon, and that is what is experienced as radiation, or what is observed as radiation. And that is exactly the analogy that I try to say, that is often repeated, but if you look into details, that is not quite correct. And like, I'm not an expert on this, so I may also, like, what I'm trying to say may also be wrong, so please don't crucify me on this. But in quantum mechanics, what you try to do is you try to find a certain state, a quantum mechanical state that describes the system. So in this sense, that is a black hole. And you try to find the dynamics of that state, how it evolves in time. And it turns out that there is a non-zero probability, because in quantum mechanics, everything goes in terms of probability. So there is a non-zero probability that you start out with a state where you have just a black hole. And a certain time later, you start that state evolves into a state where you have the black hole, but also one particle, like that particle just materialized. And that is sort of my understanding of Hawking radiation. That it is a result of quantum mechanics in curved spacetime, where as a result of the indeterminateness of quantum mechanics, you can have a creation of particles that are perceived as radiation.
Yeah. Sorry, Deanna just wrote a hilarious comment in the stream. I've put it on screen.
Yeah, there's a lot of stuff happening simultaneously here. I find it very overwhelming. So I wasn't paying too much attention.
we said before the stream and as we introduced ourselves that we're a bit tired, and here we are through our own fault. I accidentally shared it twice. Through our own fault, we're talking about quantum mechanics on the border of a black hole. I guess to sum it up, the problem is perhaps that early in the days of Hawking radiation, Hawking maybe even, or someone else came up with this kind of analogy of particle antiparticles in it. And it's something that a lot of us repeat. And I think it isn't quite a wrong analogy, but it is one that leads to these possible misconceptions, like the one that Paul was bringing out, which is totally natural. It's to say, like, why isn't it an even process? Why doesn't it equilibrate? Sometimes you get the negative mass thing coming out. I mean, you can't actually have a negative mass particle. So in that sense, like that actually exists on, the technical term would be on shell, but meaning like it actually can be detected as a real particle that doesn't actually exist. So yeah, I think maybe we can move on and just Hawking radiation exists or probably exists. It's difficult to explain. None of the three of us are actually like experts on like the inner workings of Hawking radiation, even if Deanna is an expert on the consequences of it in the context of the CMB. So yeah, thanks for the question, and hopefully maybe in the future we can get someone who is, I don't know, working exactly on this and they can talk to you about it. So yeah, now let's maybe go back to Mark's question from a while ago. I think it was on like what challenged us the most. What challenged me the most over the last 2 weeks is trying to explain Hawking radiation in a live stream. But the second most challenging thing we can talk about now. Sorry about the boring time while I scroll. It sounds like it was a great conference. What were the biggest learnings or the things that were discussed at the conference that challenged you guys the most? So I have something I have on mind, but yeah, Deanna, do you want to have a go at going first?
Sure. So I think there's been a lot of really cool things at the conference and a lot of things that I perhaps already was slightly aware of and became more excited about, like all the amazing data we're going to get from large-scale structure soon. This is something that was on my radar, but I wasn't like actively aware of just how cool it's going to be. But one thing that really challenged me, I think, was the plenary talk we had on positivity bounds in cosmology. Now, this is a topic that was completely foreign to me. And I saw the title and thought, whoa, I'm not sure if I'm going to get much of that talk because, you know, we're very good at our own fields, but you move slightly out of our field, it gets harder. And the more you move, the harder it becomes. This was about, let's see if I remember correctly, basically using some first principles, some basic things that we would expect of a general universe to have, to try to learn things about the observables we can see. So using things like locality, which we explained in another broadcast and I am not going to attempt to do today, or just basic conservation quantities or principles of the universe at a very, very fundamental level, like a universe should have these certain properties, and trying to use that to get information about the stuff we can actually see and measure. And to me, this is something that had always sounded very foreign and confusing. Now, the plenary speaker did an excellent job of explaining it, and to the point where I actually really felt like, wow, I should be caring about this topic too. I think it was probably the toughest topic of all the plenary talks because it is so abstract and it is something that is very, very difficult for us to think about at all. And I think Scott Melville, the plenary speaker there, did an amazing job of breaking that down. But that's probably the talk that I had to pause the most and think and scratch my head over, like, wait, let me just go back, watch that again, and just really try to understand it. So that was a super, super cool talk, and I definitely felt very challenged by that one.
Yeah, just I've positivity bounds feel like magic to me, because the assumptions that people like Scott are making about the sort of fundamental physics just seem so obvious and generic, and like if I didn't know the conclusions that they get to, and they said, oh, we're gonna derive the consequences of causality in the fundamental physics, causality meaning that essentially you can't affect stuff in the past, I'd be like, yeah, all right, you're going to find that there's nothing. Like, what is interesting going to come from that? But then it turns out that the structure of quantum field theory is such that if you do impose this in the fundamental physics, you actually do make quite stringent predictions about what the low energy universe will look like, which is interesting on two levels. One is that you're kind of restricting what the low energy universe we exist in can look like. But second of all, if you detect something happening here that looks like it could totally happen here, and then that is actually saying that the higher energy theory is somehow violating one of these like super necessary principles, then you're either saying that quantum field theory is breaking down, or that the more fundamental physics doesn't satisfy something like causality, which is just would blow my mind. So yeah, super interesting stuff. Matthias, any thoughts on positivity bounds, or if not, what was the most challenging part of the conference?
I find it very interesting that Diana says that was the most challenging part of the conference, because for me that was like Scott's talk was just heaven. Like, I loved it. It was the thing. Out of all the talks we had, I can honestly say that is the one that was closest to what I could claim at understanding, and like.
It's like imposter syndrome in action. There's Deanna thinking it's super difficult, and you're thinking like this was the easiest part of the conference.
Like in a way, right? Because like our backgrounds are entirely different. Because I worked in quantum gravity, and in quantum gravity you often have these very abstract mathematical constructions, and just the fact that they have these very sort of intuitive interpretations, like causality, locality, and unitarity. What you say, that you can't imagine that gives you anything interesting, but it turns out to give you very stringent constraints. These concepts you deal with in quantum gravity a lot, and because of that I am quite familiar with it. And in contrast, there was the Erisita talk, for example, or the like any experimentalist talk, where they talk about like, this is what we observed, and I'm like, guys, you have data? Because in quantum gravity there is no data, there is just mathematical reasoning and a slight bit of wishful thinking. And yeah.
I guess in some sense this is what makes Scott's work just so amazing, because he has found constraints on low energy models by combining positivity bounds and data. Like, he actually has contour plots where it's like, and here is the line. We probably should have, if we'd known we'd bring this up, actually got one of these plots. But here's the line. Everything above this is ruled out by the positivity bound. And here's the contour, which is the best fit from the data. And it's like blowing your mind that somehow some research group has found a way to actually bring what you're saying. Yeah, like stuff that's familiar to people working on quantum gravity and stuff that's familiar to people working on the data, and actually link them.
I find it a very cool topic, and like, if I have the time to really delve into it, I would definitely be keen on doing so.
Cool. Yeah. So my most challenging was I attended one of the parallel sessions yesterday, And there were a couple of talks. There was one on voids, which is actually something I've worked on quite a lot. But there was another one on assembly bias statistics. So I guess I'm a little bit like Matthias here, that when people start to get on the very observational side, I start to get a bit confused. So I've heard the phrase assembly bias many, many times and just never worked out what it actually is. And I finally learned in this talk, I finally actually concentrated in a talk on assembly bias sufficiently much that I learned what it is. And it's this idea that the history of how a universe, a halo, a accumulation of mass in the universe, how its history, whether it accumulates a lot of its mass early or late, will affect how subhalos, how different, so you've got a big accumulation of mass, and then inside that you might have local overdensities inside of it. And assembly bias says that if the bigger halo accumulated all of its mass early on, there'll be a different number of these subhalos than if it accumulated its mass later on. So assembly here is meaning like the assembly history, whether it assembled early or assembled late, it creates a bias in terms of if you assume, if you have like a sample population of galaxies or galaxy clusters and work out how many subhalos they have, you're going to get a bias if you then try and use that sample to model the entire population, because the entire population might have assembled earlier or later. And I've heard this phrase many, many times and finally learned what it actually means and how it's actually useful and interesting for cosmology because of this bias that you might make incorrect cosmological predictions if you have a sample of these halos, of these galaxy clusters or something. And another phrase I learned, fiber collisions, was something I'd never heard before, which is a very down-to-earth problem when you're trying to measure these galaxies, that you have these optical fibers. The same thing that I think it's the same. I might be completely wrong here. I think it's the same thing that my internet is being carried through, an optical fiber, but an optical fiber that is in a telescope pointing at the sky, and then the light comes into this optical fiber, and then we're able to measure the spectrum of the elements that are in this galaxy that are bringing the light. And that's how we work out how far away it is, by how much the Doppler shift has happened on this spectrum of light. But fiber collisions are when two galaxies are seen by the same fiber. So the galaxies collide in the fiber and you don't get a clean spectroscopic measurement of the elements in one of the galaxies because there's elements in another galaxy. And though two galaxies don't actually need to be near each other, they might be very far apart on the line of sight, but just in exactly the same angle. So the speaker kept using the word fiber collisions, and then I asked, oh, sorry, by the way, I have no idea what fiber collisions means. And then she gave an extremely good explanation of fiber collisions, which I'm now giving secondhand. So if my explanation's not great, it's because it's not her fault. But yeah, so learning about this sort of very observational stuff was super interesting to me. Cool. Do we want to carry on this at all? Or if not, we can move on to another thing, the next thing that we found interesting.
There's a nice question from Paul here about conferences in general.
Cool.
Do conference presenters usually present from the point of view that most of the audience is not a specialist on that specific topic? So if I can just give my answer to that, I think it very much depends on the conference, because sometimes you might go to a conference that is purely about dark matter, right? And there you go with the assumption that everybody has some common knowledge. This conference that we've been at for 2 weeks, the topic is just cosmology, so everything goes, right? And we've already seen the example here that the three of us on screen have very different backgrounds. So when I gave my talk on CMB, I couldn't assume that everybody was familiar with it. So I treated the talk as a chance to tell everyone else about what I'm working on. And I just assumed that we all have the shared knowledge of physics and some general cosmological background, but nothing else needs to be assumed. But I think for the parallel talks, so I gave one of the longer talks. For the parallel talks, you only have 20 minutes. And there you usually do have to assume that people have some common knowledge, because you only have 20 minutes. You want to explain your own work. It's not so much a review or introduction to a topic, but it's like, this is what me personally, this is what I'm doing. And there you might assume more things. Usually the parallel sessions are grouped by topic. So if you attend one on dark matter, then you assume that the people in general have this background knowledge. So it very much depends both on the conference where you're presenting and the type of talk you're giving. I think for plenary talks, they are often more reviews and kind of introduction so that everybody is on the same level. Not sure if anyone wants to add anything to that.
Yeah, just to say that the person who was talking on assembly bias was Kuan Wang, and I certainly wouldn't, say it was bad that she didn't define fiber collisions, because I had to ask her during the talk and then during the discussion time, and it took her 2 or 3 minutes to explain it at a level that I understood. And as you said, she only had 20 minutes in her talk. So these are the sort of things you kind of just have to assume that your audience already knows, and if they don't, they'll ask about in the live discussion time. Because if she'd spent, I think fiber collisions is probably something that everyone who works in spectroscopy knows, because they've heard it a million times, and it's just people like myself who haven't, who don't. And if she'd spent her time defining every word as important as fiber collisions, she probably would have spent 20 minutes just being a dictionary rather than talking about her actual original research, which was also, super interesting on all of this assembly bias stuff, and finding a way to separate to actually measure the assembly bias so that it isn't then a problem for the rest of cosmology. Okay, so now do we want to move on to a new topic? So we talked about primordial black holes, which was my topic most recently, and then we had that awesome question from Mark. So I think we were going in an order that would mean that Deanna is next on the what did you find interesting during the conference topics?
Sure. So I think we just answered the what do we find most challenging, and we also had the one at the beginning of what did we like in the last kind of few days. And I want to talk about what I found the most rewarding. To me, that was actually the non-science talks. This is something that you've heard me mention in every broadcast so far, but I think it's been incredibly important that this conference moved beyond cosmology and really emphasize that we're not just cosmologists who do cosmology, we're people. There were talks on many different topics. We had a talk on equality, diversion, inclusion. We've had a talk on imposter syndrome. We had a talk on how what challenges PhD students face. Today we had a discussion on how to write good papers. And all of these discussions are ones that you would never get at the normal conference. And they are ones that were purely promoted by general participants who said, like, hey, we want to talk about this. And the organizer said, sure, here's a time slot, go ahead. Set up the Zoom call for us. To me, this overall has been extremely rewarding. And I do want to mention the one that we had today, yesterday, I'm losing track of the days, yesterday, which I co-hosted, which was on outreach. I co-hosted this session on outreach with Katie Mack. Not gonna just say how incredible that was for me, but this was super cool. We got to talk about outreach and exchange ideas and tips and what has worked for us, what has worked for other people. How do we approach outreach? Of course, HAPS was mentioned because this is our 6th outreach broadcast on HAPS in the space of 2 weeks. I felt like the one yesterday, the outreach one was really cool for me because it felt like the collision of my worlds. I'm always very active in outreach. I'm obviously very active in cosmology. So to have these two come together these last 2 weeks with all of the live streams and then culminating in the discussion yesterday, this was incredible to me. This is something that we don't get at many conferences, and really to be able to find other people at the conference who wanted to talk about outreach, who could share experiences about setting up, cosmology groups or astronomy on tap, or let's go out and do observations. This was great. And I really think this whole aspect of the conference, the human aspect to the conference, has been really important to me, because we're not just sat together watching science talks and discussing science talks. We're also talking about things that affects all of us. And they've all been really good. I want to mention all of them. We don't have time to go into all of them again. We have discussed them all in the recaps. But to me, this whole human approach culminating in the outreach and the outreach discussion yesterday, it's really what's made the conference for me. So of course, all of the talks have been really interesting and I've learned a lot, but this human touch to the conference is what makes Cosmology from Home stand out above other conferences. To me, this has actually been my favorite conference ever, not just online conferences. This has actually been my favorite conference. So really big shout out to the organizers for that. That's a super cool conference.
Yeah, thanks for the kind words. I think on your point about the kind of topics about how we do research, I'll get to Bo's question in a second as well. But I think from my perspective as an organizer, and Matthias can either back me up or give an alternative perspective, it's like the conferences are there to make the research output of the whole community better. I mean, it's also there to make us to be happy, you know, like we don't want to make the research output better by making people miserable, but it's there to make research output better, right? And yes, one way to do that is to talk about the actual research topics and directly have better insights. But it's also to talk about how to do research better, right? How to not have to spend half your time dealing with imposter syndrome, because everyone has imposter syndrome, but people have it at different levels, right? And there might be people who are brilliant, but spend half of their time not feeling brilliant. And there might be people who write not great papers about great research because they haven't had that chance to kind of sit down with someone and talk about, well, what are the ways to get across your ideas well? So it seems like a no-brainer that a conference should have this sort of thing. I mean, I think one of the things that makes Cosmology from Home a little bit unique is that we actually stopped and spent time before we even planned the conference thinking, what do you want to get out of a conference and how can we implement that, rather than just what have other people done and how can we copy and paste that. So Matthias, if you want to just give your thoughts on Deanna's point, and then I can answer Bo's question.
Yeah, sure. I just find it interesting that there is that Deanna mentioned that it is the human aspect of the science that she found so fulfilling about this conference, because in a way, you know, science is a curiosity-driven field. It is not so much that you have to find an application for something, or that you have a very specific question because there is something that you want to do in finance or anything. It is just a question that you have about the structure of the universe. I mean, the universe now because of cosmology, but just anything about nature in general. So curiosity is really the driving point here, but often people define curiosity as a defining aspect of humanity. Like, people are intrinsically curious, and what I found is that it is very interesting that very often this human aspect is often ignored during conferences, or at least I never really got that benefit of it. Often, as Sean said, the purpose of a conference is to further or to encourage the state of research or the progress of research by sharing research. But very often, given the state of things, these talks are often just meant as an advertisement for the person that is actually giving the talk, and not so much for the furtherment of the understanding of the audience. And emphasizing that, and emphasizing the human aspect of doing research and the collaborative aspect of doing research, that is something that for me was a very strong reason to organize, to be part of the organizing team of Cosmology from Home. And I find it very cool that, well, in at least one case that came like that was understood and then was appreciated.
Yeah, I think just like in-person conferences do some things better than online conferences, and online conferences can do some things better than in-person. And I say that we modeled our conference from scratch, but obviously there's stuff that happens at in-person events that we were like, okay, that works. Let's borrow that. I think Deanna saying that this was the best conference she's attended, in-person or online, is a good thing for people organizing in-person conferences to take on board and think, okay, we have some capabilities here in an in-person event that online events don't have, but how can we borrow from a conference like Cosmology from Home and make an in-person event much better? Like, if I was to organize an in-person conference after my experience running Cosmology from Home, I would also make something quite different. I mean, I would even potentially experiment with having just pre-recorded talks for an in-person event. People can watch the talks in their own time and then show up in the physical lecture hall space to discuss, and only discuss, because, I mean, this is getting into a whole new topic, but the same reason we did pre-recorded and pre-watched talks for Cosmology from Home, that you don't want to just be sitting passively at a screen while someone's giving a talk. You want to be able to watch it in your own time. I think is actually true of an in-person event as well. Most of the time when you're sitting there and someone's giving a talk, you get onto your laptop, you start to sort of get distracted, but then if you did that in person, you watch the talk in your own time, you just come for discussion, I think it would make in-person events better. So there's two questions that have actually been directed directly to me that I kind of wanted to answer on stream. I love the fact that we're getting so many comments that we're actually getting slightly behind on the comments. It's awesome that's happening. Okay, so one question was, any discussions on peer review from Bo, because he remembers how I feel about it. So it must have been from a stream I did with Deanna before the conference, where I might have gone on a mild rant about peer review. There was
they had
one,
to cut you off.
There was one brief discussion about a platform that me and a few others have tried to produce called Cosmo Comments, where we try to make peer review more public. A very, very practical discussion about why that might work and might not work. But there weren't any explicitly about how peer review might be broken and things like that. Partially because no one suggested it, but I didn't suggest it myself because as an organizer, I kind of didn't have the time to invest in something like that. So if someone else didn't suggest it, I wouldn't have participated. But yeah. And then the other question directly to me by Paul was, have you thought about a perpetual conference, something like 1 day per month? Yeah, definitely. Matthias and I actually have a slightly independent to Cosmology from Home thing that we've only run one of these, but I think I personally want to do it more often, and this conference just kind of got in the way of organizing those things. But I have a YouTube channel called Cosmology Talks, where once a fortnight I interview researchers about their work at a technical level. If you like these live streams, you might enjoy Cosmology Talks. It is aimed at the technical level, but if you pause it and do a lot of Googling, you might get stuff out of it. But the idea was to take the people who've given those talks that are then pre-recorded and watched and structure mini workshops around that, like a 3 or 4 hour thing on 1 day a month, where people come together and talk about the content in, say, 2 of those specific talks. And yeah, the one that we ran was on modified gravity. In fact, we've been talking about Scott Melville a lot. Scott was one of the, was it? No. Yeah. Scott was one of the speakers.
He was,
but he didn't make the workshop. Yeah. So he was a speaker in a Cosmology talk on this positivity bound stuff, and his collaborator Johannes came to the mini workshop. And it went really, really well. The feedback we got from it was great. But yeah, organizing a 2-week conference with 350 participants is a big task. So organizing monthly mini workshops went on the back burner. But I think, yeah, my intention, and I hope Matthias's intention as well, is to get back into doing that more regularly once Cosmology from Home is over, which is now. So hopefully in the next couple of weeks. Cool. So I haven't been keeping track of the questions while I've been saying that. Are there other questions we want to address, or should we go on to another thing that we found interesting during the conference?
I think we've addressed most of the comments.
Okay, cool.
The great Daniela's joining us.
Yeah.
Awesome.
Shall we wait for Daniela, or do we want Matthias? Do you want to talk about something that you have found interesting during the last 2 weeks? Maybe you go, Matthias, and then Daniela can.
Yeah, sure. I mean, at the moment I'm just going through the schedule because the entire thing was such a blur in a way, and I mean, not in a bad way. It's just that there was a lot of information.
Okay, cool. Yeah, I think Daniela is actually now ready. So Daniela, do you want to introduce yourself?
All right.
Hello, I am Daniela Sade, and I'm a postdoc at the Institute of Cosmology and Gravitation in Portsmouth, and I do cosmology, a bit in between theory and observation.
Cool. Putting you on the spot a bit, you've only just arrived, but we were going through stuff that we have found. So we're recapping the whole 2 weeks. Anything, it doesn't have to be the last couple of days since the last recap. Anything in the last 2 weeks you found particularly interesting at Cosmology from Home and would like to share with the audience?
Well, I loved Catherine Heyman's talk. I loved the way she was presenting things, her particular point of view. It's difficult to put into words, but sometimes you hear one of these lectures, and I mean, in theory, it's stuff. Maybe some of the stuff you already know, but it's really the completely different point of view. You know, sometimes you hear some of these people, and they make you see stuff from almost a perpendicular point of view, and I mean, that was amazing. That was amazing, I think. I'm not sure I can say in words one particular things, but I think it was really I think it was like I was seeing stuff in 2 dimensions and I'm seeing it in 3 dimensions. I think I'm looking at the same stuff in a much better way. I'm not sure I can get any particular example. Then this said, I mean, I particularly like the atmosphere, I would say the friendly atmosphere in which we were able to talk and discuss between ourselves. Maybe it's because most of us were juniors, so it was relaxed. But I think there was really lots of freedom, lots of confidence in discussing, not the usual. I mean, I suppose in-person conferences, sometimes there's always some shyness, some awkwardness, when you want to talk to someone and you don't know that you can. And somehow, maybe because we've been separated from other humans for so long, it felt like people actually like to talk to one another. I don't know, that was a feeling I had. Maybe if you want, it's also the protection of being online. Maybe sometimes you feel a bit awkward in person, but under your screen, it feels less exposed. I don't know. But somehow I felt it was a very nice atmosphere. It was very nice to talk. And of course, I loved Diana's plenary. She gave an amazing plenary on the CMB and everybody liked it. Can we talk about that? Oh, yeah.
I was waiting for the CMB to show up.
Yeah. No, that was really awesome. Is it going to stay on YouTube afterwards?
I gave permission for it to be made public, yes.
Okay, yeah, that was a pretty good lecture. I think I organized the journal club at my institution. I think I'm going to tell the PhD students to go and see it, if you don't mind.
Just point out to them the place where I have the wrong word, which bugged me so much, and I almost re-recorded my whole talk, because at one point I said relativistic instead of non-relativistic. And I actually considered re-recording my whole talk for those 3 letters, and I was talked out of it. So yeah, apart from that, I was very happy with my talk.
Yeah, it was very, very nice.
Cool. In future, for a pre-recorded talk, you can just like edit that part so that a big text box comes up saying non-relativistic !
Yeah, I had to ask one of you organizers to cut out the first 2.5 seconds of video for me because I couldn't figure it out, despite trying 5 video platform software editing tools. So yeah, I thought about adding a box and decided it was beyond my abilities.
We ran a test panel event before the conference on to try and experiment with the way we were running the panel events, because in the conference we had this expansion rate H0 panel and the primordial black hole panel that we've already talked about a bit, and I was the host of that one, and it was at like I think 5 or 6 in the morning my time. I was very sleepy, and I made a similar mistake. I was kind of trying to talk about how we need a model for everything, and we even assume a model when we're talking about how stars work, and I said, we assume chemistry, which made total sense at the time, but of course chemistry has nothing to do with how a star works. It's nuclear physics. So when we uploaded that talk, there's now a big text box that says, I'm sorry, I made the mistake. Yeah. Okay. Yeah, Matthias, I kind of put you on the spot just as Daniela was arriving, but maybe you now have something you want to add about what the next thing that you found interesting during the conference was that we could talk about for a little bit.
So the point is, I just find the whole thing interesting because we tried to put the conference at the interface of observation and theory, and I'm very, very heavily a theory guy. And I find basically all the observational talks very interesting, but simultaneously find them very difficult to understand because there's simply so much data that is being collected, and nevertheless I've had very little experience with actually talking about data and trying to understand all the fancy plots that people make. So I think in the next few weeks I'll definitely try to watch those videos again and try to think about what it actually means, and that physics is an empirical science, right? What is central is the experiment, and because the experiments actually tell us what the structure of nature is. But somewhere down the line, I went into this this very mathematical and theoretical field, which has its own, like, I find it very interesting and very fun to play around with. But you sort of lose track of what physics actually is. It's not a mathematical thing. I mean, it's a mathematical science, definitely, but it's not mathematics itself. And you should definitely think, like, what for me is a learning moment is to definitely think more about data and the actual observations that you have in cosmology.
Cool, that's awesome. I mean, as you know, because you obviously co-organize, we tried to frame it as theory meets observation and observation meets theory. So for even one of the organizers, it's achieved its goal of theory meets observation. So we've got less than 15 minutes left in the broadcast now. I think there's one of two directions we could go now. Daniela, you obviously arrived quite late. So if there's any specific thing that one isolated thing during the conference you want to, what's the word I'm looking for, like bring up and talk about, that would be cool. Otherwise, Deanna has mentioned in a private chat that she wants to ask a question to all the panelists. So I'll give Daniela you the chance just to talk about a specific thing in a little bit more detail if you want, but otherwise Deanna can ask her mysterious question that is giving me a little bit of anxiety.
Yeah, me too. Did you mention the diversity part?
I think Deanna mentioned it in a kind of more general, all of the things that weren't explicitly science, but we didn't talk about diversity explicitly. So yeah, feel free, please do.
Yeah, so I would just like to mention again, I don't know who the people listening are, so I will keep saying this in the hope that one day someone listens to this and it's useful. We need all the different backgrounds to be represented in science, and this is essential in order to have the best scientists and the best ideas. The history of science has shown time and again that it's when we get the widest pool of ideas that science really succeeds. We need diversities in ideas, in person, in color, race, religion, whatever. We need everything. The bigger the pool of our ideas and the better the science we can get. So if you're listening to this and you've never seen someone looking like you in the media represented as a scientist, if you are concerned that you don't think of yourself as a potential scientist because you don't think you look like one, please realize this is a bias that was implanted into you and into the wider society. It doesn't make any sense. If you don't see someone looking like you in science, we probably need someone like you, okay? So that was the most important thing. And then something else that we already highlighted, and I think it's just worth highlighting again because, you know, it's never too much. It's important, especially in this situation, to look after your and each other's mental and physical health. So let me remind you again, it is fine not to be okay occasionally, but fortunately you can do something about it. So if you're a PhD student, some estimates suggest that up to 30% of the PhD students satisfy the criteria for depression. But fortunately, there are things like therapies or medicine support groups. There's really lots of stuff, and more likely than not, one of them works for you. I mean, it's no longer something you can't do anything about. These things work. So there is no point in suffering in silence and being miserable when you can actually do something about it. And if you've been taught that the honorable thing is to suffer in silence and hide it, maybe it's honorable, but it's also very stupid because you can actually do something about it. And suffering for nothing is rather irrational than honorable. So we already said this, I think 2 sessions ago, but I just think, you know, it takes 5 minutes to say this, so why not? That's it.
Oh, that's fine. I mean, this is a recap of everything, so we can repeat stuff. And I agree that what you mentioned is super important. So thanks for bringing it up. And it fills me with warmth that our conference was able to provide this platform that people used and got out of it to have that conversation. Okay, Deanna, put us on the spot. What's the question?
Right, so every plenary speaker was asked to summarize their presentation in 1 or 2 minutes. Every parallel speaker was asked to summarize their presentation in like 30 seconds. So I want to ask everybody what is your take-home message from the conference? So 2 weeks, one take-home message. I'm curious if we can summarize 2 weeks into one sentence. I do have one. There's a quiz. Yeah, there's a quiz, Bo. I just put them on the spot with that. Who wants to go first?
You can go first if you already have one while we think.
I think a big takeaway for me has been that there is so much still to do in cosmology, and we're doing it together. Like, there are so many aspects where cosmology is going for it. There is so much new coming to cosmology in the future, so many more data sets, and we are all in this together as a collaborative group. So my take-home message from the conference has been that cosmology still has so much to tell us. The future is bright, and we're going to discover it together, which is a nice takeaway from a conference.
I feel like I have something I can say, so I'll let Daniela and Matthias keep thinking. But one thing on the organizational side is that online conferences can work if you put some thought into them. And okay, apparently, according to Deanna, can even be better than in-person conferences. And in-person conferences could learn some stuff from online conferences. I don't think that the long-term future is only online conferences. There are definitely stuff that can be done in an in-person conference just because you're in person and you're there that won't go away. But for things like climate change, even once the pandemic goes away, more online conferences probably wouldn't be a bad thing for the planet. I'll try and think of a physics takeaway as well. But Matthias or Daniela, do you have a message ready?
I do. And in fact, Sean, to be entirely honest with you, I didn't know that the conference was going to be so good. And to be honest with you, I thought that because it was an online conference, I had planned much more time to do my usual work. I didn't know that I would spend so much time doing conference stuff. So I found myself in trouble because now I'm behind with work because I realized that it was actually all useful.
You're welcome and sorry.
No, regarding the take-home message, I think, especially because there had been less interaction, again, due to COVID and stuff, I think I hadn't realized just how fast the cosmology had progressed in some areas that I'm actually interested in. So basically, at the beginning of 2020, I wanted, say, XYZ to be done. And some of the things have actually been addressed at this conference. So maybe they're not ready yet. Maybe it's work in preparation, but it's going to be done. And that was interesting, I think. It was interesting to see how much stuff had been done, actually. I mean, of course, you read the papers, but it's not the same thing, right? You can never read all the papers and all that it's useful to know. So I think one interesting thing I've realized is that stuff had progressed much faster than I thought it had, which is good.
Cool. Matthias, your turn.
So I honestly feel that my takeaway is a bit trivial compared to all the other things that have been said now, but I find it very, very, like my takeaway message is that it is okay not to be apprised or to be fully informed about everything. And there is a lot of stuff that people work on and a lot of stuff that has to be done, but there's also a lot of stuff that people don't know, and that's okay. And that actually means that there is a lot of stuff that you can figure out on, can work on to figure out. It's okay to play with the things you don't understand. You don't immediately need a justification for it. Only if you want to make it a bit more firm and want to make definitive statements and predictions about that, then it would be useful to have a justification for it. But it's okay to play with things. I feel it's a bit silly, but on the other hand, in the time that I was a PhD, I often found that I actually did needed to know all the things before I actually tried to solve problems, and I find it very refreshing to see that it is okay to be a bit more frivolous with things.
I think it's an awesome take-home message. Not
yeah,
silly
not
at all.
only is it okay and not silly, but if you say it with that tone of poemody, of sort of cursed rock star, I mean, how is that not relevant? You're basically looking like some kind of Jim Morrison.
Yeah. So I mean, we have been talking about imposter syndrome before, but I mean, you can't read people's minds, right? And like everyone else, like you only see the collective of everyone else's knowledge, and you only know the little bit that you know. And I don't know. I just felt that that was my take-home message, and it's just that I guess I'll just leave it at that.
There's some quote from I think it's Ernest Rutherford or someone from his approximate time, and I'm going to just paraphrase it in 21st century language, but it's something like, "Of course we don't know what we're doing. That's why it's called research," or something like that. That kind of encapsulates this idea. I mean, maybe we should end on Matthias's comments, because mine is going to be way more like practical and specific than that, and that was a really, really good message. But one thing I want to highlight that we haven't had a chance to highlight, and it's not the sort of thing that gets highlighted in an outreach stream like this, so I just want to take some time to highlight this, which is the people who do wonderful work on making better mathematical techniques. And there are two talks during this conference, one that I was aware of before the conference and one that I happened to just attend and learned about because I attended that parallel session, that have made huge progress on specific techniques. And I'm going to try to give a way of explaining this to the audience so that it is satisfying. But one was these endpoint correlation functions. So we talked about correlation functions earlier. If I know the density here, a 2-point correlation function tells me what the density here might be. A 3-point correlation function says if I know the density here and the density here, what the density at some third point might be. And these are notoriously difficult things to calculate. But one group that presented their work here has shown how instead of it, if you've got an n-dimensional and correlation function, sorry, an n-point correlation function, you expect it to take, I think it's normally like n cubed amount of time to calculate. And these guys have reduced it to n squared, which, or maybe even smaller than that. I can't remember the details, but they've made essentially calculating these important observational things, instead of taking enormous amounts of time, be able to happen much more quickly. And another group that were doing something called a Monte Carlo Markov chain, that is a way of calculating probability distributions, which would take me 5 or 6 minutes to sort of explain how they work. But these guys have come up with a technique that allows you to find the variables that you should be doing your Monte Carlo Markov chain of much, much more effectively. And I think, so the first group, the speaker at our conference was Oliver Philcox, and the second group, the speaker at the conference was, let me check my notes, was Minas Karamanis. So I just want to pinpoint those two people who gave great talks. And I think Deanna says there's one thing she wants to highlight before the end, and we only have 2 minutes left. So Deanna, take the floor and finish off the live streaming of Cosmology from Home 2021. It's probably appropriate that you're finishing it off, given that it's your audience we've been speaking to these last 2 weeks.
Yeah, and I actually want to talk about outreach again. And I want to thank the two organizers here on screen and the ones not here for doing so much outreach this conference, because often conferences try to do outreach and it's like, we do one public lecture, that's it. And this is our 6th live stream. We've had over 9,000 views just here on HAPS. We've had an Ask Me Anything that had over 3,000 upvotes, over 600 comments and questions. This is amazing. This was not something that I think was planned for a long time. It was thrown together a bit last minute and it was amazing. And I just really want to thank everybody who's joined these live streams. I've been nagging people for the last 2 weeks, getting everybody on board. Most people had never done this before, and we've had people join several times. Like Danielle, I think it's your 4th time with us already. And it's been amazing to see so much outreach, and I am always advocating for much more outreach. And seeing this conference have 6 live streams in 2 weeks, that's absolutely incredible. And I also want to say a big thanks to the HAPS team for letting us take over the HAPS account last week, because that did help us reach a lot more people and just bring the science outreach to so many more people. And as Daniela says, we don't know who's watching, but maybe we've convinced somebody to come join us in Cosmology. And for me, that is what outreach is about. So big thank you to the organizers for putting on these 6 broadcasts, and to everybody who's participated in them, because this is honestly been absolutely exhausting, but also absolutely brilliant fun. And Sean has been on all 6 of them, as have I. So I think we're all ready to call it a day with live streaming now. But really, thank you to everybody who's participated in these live streams.
Woo!
Yeah, thanks. Thanks. I think that's a perfect note to finish on. So thank you, everyone, and goodbye. See you in the future.
Bye.